Okay, so we will look at this side of the paper. Okay, October, November 2020, variant 2. Okay, let's look at the first question. So this is to find the Maclaurin series. Okay, we have got the tangent x plus 1 over 4 pi up to and including the term in x squared. So if they need until the x squared, it means that we need to actually like differentiate it until we have got the second derivative. So basically differentiating this is not so difficult for us to actually do. So once we differentiate first time, we are getting a secant square, okay? And another time when you actually differentiate, right? So from here, when we differentiate the secant square, we get like 2, and then we got like a secant itself. And then differentiating the secant will give us a secant tangent. Okay, so this is why in our expression here, we actually have got like this 2 secant square and then with a tangent there. So after that, what we need to do is just, okay, because we want to get all the coefficients in the series there, so we sub in x equals to 0. Okay, so we evaluate all the values from there. Okay, so we get like, in this case, like a 1, 2, 4. So those 1, 2, 4, we are going to substitute that into the formula for the Maclaurin series. We don't really need to memorize it. Okay, we can just get them from the MF19. Okay, so this is the value that we will get, right? Okay, second question. Okay, so this is what we have. Okay, a curve has y is equals to cos x, and we need to find the surface area generated. Okay, when we actually look at the curve when it is generated. Okay, about the x-axis. So we've got, okay, the y is equals to cos x here, which we can actually do the dy dx. We can differentiate it, and then we can actually simplify that by looking at the square root of the 1 plus the dy dx square. So this is part of the formula that we have, okay, in the surface area. So when we actually square the dy dx and add it with 1, it gives us a cos square. So the cos square here can be cancelled out with the square root there. So we actually get a cos from there. And after that, what we see is, okay, we now look at the surface area. So for this surface area here, the formula would be 2 pi y multiplied by square root of the 1 plus dy dx squared. So what we have for the y here is that we have got cos. Okay, so cos and then multiply by another cos here, so we get a cos squared. So as usual, okay, change that to the double angle. So once we have got the double angle already, it's very easy for us to integrate. So the cos 2x becomes like a half sine 2x, and we have got the 1, which will actually we will get x after we integrate. Basically, the work after that is just to sub in the values. So when we sub in a half, we get like half sine 1 and also a half. When we have got the 0, both terms are 0. So after that, just use the definition for the sine 1. Okay, so tidy up a little bit. So this is the expression that we will get. Okay. Next. So find all the roots of the equation w plus 1 power 6 is equals to 1 here. So giving your answers in the form of like an x plus yi, okay, where x and y are real and exact. So here we have to look at like, okay, the w plus 1. So the w plus 1 is equals to the e of, okay, so this is 2p pi over n, right? So we have got here the n is the 6 here, so that is giving us like a p pi over 3. So the value of the p that we have here is like p from 0 to 5. So because now we actually want to solve for the w here, so we can actually move the 1 to the other side here. So we get e power p pi over 3 I minus 1, where the p is actually from 0 to 5. So basically, when we actually have got this form already, right, we could just sub in, okay, all the values of the p inside there. So once we actually have got like all the values of the p, which we substitute that in, so for each of the angles there, the arguments there, so this is when p equals to 0, we get 0 for the angle or the argument there. So that's why this gives us a 0. And also the rest of it, like, okay, when we have got the e power pi over 3i. So this is like, okay, we just have to write them out, okay, by using the polar form. So this polar form, because we can actually calculate the value of like cos pi over 3 and so on, right? We could really evaluate them and minus that with a 1. So we just have to do the same thing for the rest of it. So basically, it's just everything can be actually evaluated such that we're actually able to get the form, which is like the x plus 1i form. Okay. Okay, so let's look at the next question. Find the solution of this differential equation. Okay, when the y equals to 1 and y equals to 3 and x equals to 1. So for the first step that we need to do is, okay, we need to look at the standard form. Okay, so because we have got like an x, okay, before this dividing x here, so we need to actually divide the whole thing by an x here. That's okay, we're actually getting what we need in the integrating factor. So in the integrating factor, we actually need this. So we actually have got like, this is an e power integral of the 2 over x. So integrate 2 over x gives us like a 2 ln x. So 2 ln x here actually gives us like a ln x squared here. So when we have got the e power ln x squared here, so we actually have got like a x squared. Okay. So after that, what we need to do is we just need to multiply this x squared. So remember, it's to always like multiply this x squared to the standard form. So this is the first line that we see. Sorry. So after that, okay, the left hand side, no matter how complicated it is always like we have got like a x squared, which is the integrating factor, to multiply by the dependent variable, which is the y. And when we actually multiply, okay, the right hand side will just become the x e power x. Okay, so from there we can just integrate both sides. So this means we have to integrate the x power e power x. Okay, so this is, we just have to use a little bit of the by part to integrate it. Okay, so if you use the by part, this is the result. So after that is to actually solve for the constant. So we can sub in x equals to 1, y equals to 3. Sub in there, and the e terms cancel off nicely. So we only have got like c is equal to 3. So basically just to rearrange, okay, because the question really want us to give like y in terms of x. Okay, so just move that x squared over to dy. So you could either leave it in this way, or you could just write over x squared the whole thing there. Okay. So in the next question, this is a differentiation question. So we have got the equation which is given by this y squared, xy plus 1 squared is equals to 5. So show that at the point which is at 1, 1, the dy dx is negative 2 over 3. Basically, this is not something that is very complicated for us to do. We just need to be careful about like the bracket here. Okay, the first one not really an issue. When we differentiate y squared, we get 2y, and then we have to multiply by the dy dx then. So not really an issue there. For this, okay, this is the thing. So we need to differentiate this xy plus 1 with a square. So the method that we differentiate then is bring down the power. The expression still has the power 1. And after that, right, we need to differentiate whatever which is inside the bracket. So it means that we are going to differentiate like an xy, okay, inside the bracket there. So as we differentiate the xy, we need to consider using the product rule, okay? So when we use the product rule, it is giving us like a x divided dx plus a y. So of course here you could simplify a little bit by dividing the whole equation by 2 if you want. So after that, right, okay, because you see this expression, it's very difficult for us to like make dy dx as a subject here already. So we don't need to bother to make dy dx as a subject here. Since they only want value, so we just sum in the value, the xy here, okay? So we're actually trying to solve it a little bit, then we're actually able to prove that the dy dx is negative 2 over 3. So that's for the first part. So, okay, now the thing here is we are going to do the second derivative. So for the second derivative here, it would be slightly more complicated already, okay, because we are going to look at like the product rule, okay, even more. First term, we may actually consider doing the product rule, right? So we have got to differentiate each of that. So for the first term here is we differentiate the y, so we get dy dx, but we keep the dy dx, so we get the dy dx squared here. Second term here is we keep the y, we differentiate the dy dx, so we get y d squared by dx squared. Okay. For the next two terms, that is like, okay, we keep the xy plus 1, then we actually differentiate these, okay, the x dy dx plus a y there. Okay, so it's to use lots of the product rule to actually do that. After that is we are differentiating the xy, xy plus 1, keep the this, okay, x dy dx plus y there. So certainly from there, they are something that we could actually sort of simplify a little bit first. Like we can actually add up the 2 dy dx term here, and then we have, this is actually the same thing multiplied together, so we can just give it a square there. So we want to find the value, okay, when we have got the 0.11. So this expression here has got the xy and also the dy dx, okay. Our aim is to find the value of the d square y dx square. So as we actually sub in the xy and also the dy dx there, so we're actually able to find the value of the d square y dx square from there accordingly. Okay, so it's not something that is super difficult, but just that you have to really work on the expressions carefully. Okay, right, let's look at the next question. Okay, so this is some typical second order differential equation again. It's 11 mark. So if you look at the left hand side, okay, so left hand side gives us the auxiliary equation. So we can actually solve the auxiliary equation, then r equals to -3 and r is equals to -5. Okay, so with that, we can actually write out our complementary solution. So this is our complementary solution. Okay, it's xc. So remember the variable here has to be like matching with what we actually have there. So it's x in terms of t. Okay, so this is our xc here in terms of t. So after that, okay, it's the xp. So the xp is actually looking at the right hand side. Okay, so we have got the cos 3t. So when we actually form the xp here, the particular solution here, we need to actually have both the cos and the sine there. Okay, and after that, we just need to differentiate 2 more times. Okay, so we will actually have the expressions here, okay, until the second derivative here, that we need to substitute that into the expressions. Okay, we need to substitute that. So it's to tidy up later on. Okay, so we have got the coefficient of the cos and also the coefficient of the sine that we need to solve it. Okay, so we can first look at the coefficient of the sine there is 0, so we get b in terms of a, and then we just need to sub in and solve that. So the a here gives us a 1, so here the b is actually a 4. Okay, so this is what we have for the xp. So after that, okay, we want to solve the everything, yeah. So we need to actually put it back, okay, the xp and the xc together. So this would be the solution for the differential equation. So now they actually gave us some value. Okay, so t equals to 0, x equals to 1. Sub in, get one equation from there. Another thing is we need to differentiate that. Okay, we need to differentiate the x here until we get the dx dt. So by using these values, t0, x1, dx dt is a 0. And we sub in and we can actually solve the c1 and the c2 here. So with that, okay, then we are actually able to get the general solution for this. Sorry, the particular solution for the equation there. Okay, so this is the whole step. Okay. If you look at the next question, it's a complex. So show that we have got this expression here. Okay, the sum of the set power 2r from r equals 1 to n is given by this expression. So basically, it is to, if you are not sure like what is actually the first term or the ratio from there, right? Okay, we can actually like just write down the first few terms. Okay, and we notice that okay, this is actually a GP, the sum of the GP. So for this sum of the GP here, we actually have got the first term. Okay, it's z squared, and then when we come to the next term, the ratio here is actually a z squared as well. Okay, so just sub into the formula. So this is a r power n minus 1, r minus 1. So from there, tidy up a little bit. So we're actually getting this expression here, which is just one step further from like what we actually need here. Basically, we just need to divide by the z, or we multiply by the z power -1 for that, so we can actually achieve this thing already. Okay, it's just a 2 marks question for that. So from there, okay, so by letting the z is a cos theta plus a I sin theta, so and show that if the sin theta is not equals to 0, this is the result. Okay, so why is it we have got something like this here? So first, okay, is to actually sub in the z into the earlier left-hand side first. So we notice that, okay, this is actually what we have for the left-hand side there. Okay, and for now, right, okay, we already also like proven this is what we have in the earlier result there. So we can just actually like write out everything from there. So the z power 2n plus 1 is actually this. Z is actually this. Okay. And for the denominator there, why they actually purposely ask us to actually like express into this form, the reason is that it is actually a nice result. Okay, it's actually a 2i sine theta. Okay, so we want to get rid of the I in the denominator. So we can actually multiply by either I, or for me, I'll just multiply by negative I from there. It's up to you. But after that, once we actually tidy up everything nicely, so we will actually have got like one real part and also the imaginary part. So in this case, what do we actually need to prove? We need to prove for the cos here. So the cos is something related to the real part. Okay, so we take out the real part. So the left-hand side for the real part is the sum of the cos 2r theta. And here we have got like the real part is actually this expression. So the sine 2m plus 1 theta minus sine theta divided by 2 sine theta. So we tidy up a little bit. Okay, so this is actually what we get. We just have to rearrange from there. So once we actually rearrange from there, okay, then this would be the result that we could actually show, okay, by using the real part. Okay, it's not like, I mean, usually the question will just ask us to actually prove this, and then it actually has got like this kind of expressions, right? Sometimes the question might not use this form. They might actually like going a bit further and ask us to express it into some other form from there. Okay. So, okay, let's look at the next part. So this is the question that is actually about the area of the rectangles. So this one has only one part and it actually costs us like a 10 marks for the question there. So let's see, okay. The diagram that is given is usually for the first part, but since it only has one part, so I mean, we just have to like rely on this diagram here. So let's see, the left-hand side, okay, here, it's actually the sum, okay, the series here. So we just need to look at, okay, whether this sum just like represent our rectangles completely. So we can look at the height of the rectangles. So this is the height of the rectangles when the x is equals to 1, until the last height of the rectangle that we have here is for the n. So it is exactly what we have, okay, for the summation here. So just to be sure, you can actually list out the area of the rectangles, and then you just show that, okay, it is actually like what we have exactly at the left-hand side here. Okay, so after that, it is to compare, right? So we need to compare these rectangles with the area under the curve. So the area under the curve here is going from 0 to the n. Okay, so we need to integrate that function. So we got to integrate the function from 0 to n. So in the denominator there, it is actually something that we are quite familiar with. In fact, we just need to complete the square from there. So once we complete the square, we recognize that this is actually the x squared plus an a squared form. Okay, so for this x squared plus an a squared form, it is giving us an arcshine. Arcshine of the x over a, right? So we have got the n, and then also we have got the 0 that we need to sum in. Tidy up from there, this is what we get. We sum in, okay? So when we actually sum in, it actually gives us all the arcshines there, okay? So this is the arcshine of the 2n plus 1 over 3 that we need to actually like calculate that by using the log form of the arcshine. Same thing that goes to this one here. The arcshine here we need to calculate, okay, by using the log form of the arcshine from there. So we just need to tidy up here. Okay, let's look at the one that is at the second term here first. It's actually quite nice though when we actually try to simplify them. So this is actually what we get. Okay, it's actually quite nice. So it's actually giving us like a ln of 3 over 3 there. So after that, it is just to like combine everything, okay, carefully. So we will actually have got like this is actually the final answer that we could actually get from there. Okay, so it's about simplifying the things there, yeah. So you just have to look at those things carefully, okay, and simplify them carefully. Then you actually get the result from here. Okay, it's already being like given in the question there. Okay, you just have to simplify them carefully here. Okay, so okay, this number 9. So this is, we have got A is a positive constant. Show that the system of equations, okay, that has unique solution and interpret this solution geometrically. So it's always like, okay, we want to show that it has got a unique solution or no unique solution. It's always about the determinant. Okay, so we just need to take out what is the determinant here, and we have got this is like a 4A. So, okay, why does this 4A gives us a unique solution? We need to explain it. Okay, so because the given value of the A here is positive, so the 4A is also positive, so we cannot have the determinant is equal to 0. So if the determinant will never be 0, so the three planes here, they must actually intersect at a single point. Okay, so this is like they ask us to interpret this solution geometrically, yeah. So we need to actually mention about like how does the three planes looks like. Okay, so in the following part of the question, so we have, okay, now we suddenly have got other matrix here. So sometimes it might be related to the previous part one. Okay, so you see here it's actually related to the previous part. So not sure whether they will be related later. Okay, so let's just see. So the first one, it looks quite standard. It should show that the eigenvalues here would be A, -1, and -4. So it's very easy, okay? When we choose the first column to expand, it actually gives us quite a nice expression already. So from here, we can easily prove that the eigenvalues are actually these three values here, okay? So now, okay, when we actually want to find the matrix P here, it is to look at like the cross product, okay, of any two rows. So because we want to find the matrix P here, right? So it's about the eigenvector. So for the eigenvector that we have here, right, we need to actually like sum in the value of A each time. Okay, so we sum in the value of A from there. So here's the thing. When we actually sum in the values of the A, right, for this case, it's going to be a lot of the A's there. So it would be sometimes a bit complicated for us to actually work on the cross product. So remember the cross product here is we will choose two rows. But when we actually choose the rows, right, just choose it like smartly, where if we choose the second row, it's a 0, A plus 4, and 0. So basically, we could simplify the multiples first before we do the cross product. Because if we didn't simplify, when it comes out lastly here, right, it will also be able to be simplified. Okay, so might as well be simplified earlier because this one is very complicated. It has got an A. So we can actually simplify. We can afford to simplify that. Okay, it's not going to give us wrong thing. We can simplify first. So of course, the good choice is actually choosing the second row, okay, together with either the first or the third row, but I guess third row is easier because it has got less A to work with. So choose the third row there. Okay, so when we actually carry out the cross product there, this is what we get. Okay, A plus 1, 0, 0. So it could be simplified, right? It could be simplified until we get like 1, 0, 0 only. The rest of it is the same. When lambda equals to -1, okay, this is the lambda I minus A that we get. So of course, no choice, okay? We could use like the first and the second or first and the third. But again, when we actually look at the second and the third row, right, it's having like a -3. So it's like 0, -3, -3. That when we actually try to do the cross product, we could simplify that first. Okay, not necessarily we need to keep the -3 because we can use any multiple of that. So it will actually like come out quite straightforward. So we actually see we have got this result here, which we can actually divide by the A plus 1 so that we can actually get this eigenvector here. Okay. So with that, okay, the last one is a similar thing. So we can see the second row is everything 0, so we can't cross it. If you look at the third row, is 0, -3, -3, which could be simplified until we get a 0, 1, 1. So when we actually do the cross product from there, it is easy. So if you look at these expressions here, it is actually a multiple of like A plus 4. Okay, something like that. So we could actually look at it in this case. Okay, this is one of the possible eigenvectors from there. So later on, we will actually be able to obtain these P here without anything which is in terms of A. Okay. So, is there any continuation to the question there? Yeah, okay. So use the characteristic equation of the A here to find the A inverse. So characteristic equation is actually coming from the eigenvalues. Okay, so these are the eigenvalues which we can actually make them into factors. And then what we need to do next is we just need to expand. Okay, so once we expand, this is the characteristic equation. So from the characteristic equation here, we could sub in the matrix A. And remember, for the constant for A here, we just need to add the identity matrix to this one here. And okay, what we see later on is that, okay, we want to get A inverse, right? So from the A inverse there, we just need to multiply the whole equation by A inverse. And we try to make A inverse as a subject here. Okay, so this is a question where they are trying to make us like not using the calculator. They are trying to test us, okay, on our real skills, calculating skills. So here we can't use the calculator at all. So we just have to be a bit more careful, okay, whenever we are carrying out the calculation here. Okay, so in this case, you see, we need to have, for the A inverse, we need to have the A squared. So we need to calculate the A squared first. So it's advisable to actually work on the A squared separately. Okay, so I mean, although the A here, right, they are actually in some constant A, but if you really want to check the answer, right, you can actually get this expression here first, then you just sub some A into the matrix here, then you use your calculator to check the answer whether when you sub in an A into your answer, whether it matches your answer or not. You can actually do something like that, okay, if you really want to check. So after that, okay, so after that, we will just have to carry out the calculation from there. So we have got the A squared plus 5 minus A times the matrix A, and then we have got 4 minus 5A identity. So a lot of the work to do, you do your own work. So at last, okay, the 4A will move it to the other side to actually divide. So if you actually multiply it, it's super ugly. So we just leave it outside there. So this is actually the A inverse. Okay, you get this expression. Like I said, if you really need to check the answer, sub in some A, and then you check against with the original matrix here. Okay, it's the original matrix. You can sub in the value of the A inside here. Say you sub in 1 or sub in some larger value and see, so you can compare when you use the calculator whether it matches the value that you have in the answer here. You can always do that. Okay. So for the last question here, it's quite a bit of work to do. Right?